Okay, I'm going to go through the Edexcel A-level Chemistry Paper 1. This is the specimen paper from the new spec when it came out in 2016. Specimen papers, sometimes the questions are a bit funny because they haven't been subject to the same quality control as proper papers, and also they tend not to use up their best papers just on the specimen. They save them for the real thing, so bear that in mind. Right, so this question is about the bonding structure of molecules. Which element exists as discrete molecules in its solid state? It's got to be iodine because that exists as I2. Aluminium and sodium are both metals, and silicon is giant covalent, very like diamond. Okay. Which compound has non-polar molecules? Right. So ammonia, NH3 does, big electronegativity difference. Hydrogen sulfide does, smaller, but still sulfur is more electronegative than hydrogen. Water is obviously very electronegative, it's very polar. Carbon dioxide is not polar, even though oxygen is much more electronegative than carbon, because the carbon dioxide molecule is symmetrical, because it hasn't got any lone pairs around the carbon, so it's a linear, symmetrical, so symmetrical molecules cannot have permanent dipoles. So that's the answer there. Right. The best reason why HF has a much higher boiling temperature than HCl, well, it's obviously because HF can form hydrogen bonds and HCl can't because chlorine is not electronegative enough. So there are intermolecular hydrogen bonds. That is the answer. Okay. Right. Here about shapes of molecules and electron pair repulsion theory. These two questions sort of go together, 1 and 2. All right. So explain the shape of this molecule. So what we have got 2 bond pairs, and we've got 1 lone pair. So with 3 pairs of electrons, they are going to be spread out as far as the repulsion theory says they try and get as far away from each other as possible. So they're going to go roughly in a trigonal planar shape, but we have got a lone pair here. All right, so this is a bonding pair. This is a bonding pair. The lone pair is more bulbous in shape. Okay, so the shape of this molecule is going to be V-shaped. And then we'll talk about the bond angle here. Well, normally if you have 3 bonding pairs, the bond angle is 120. But one of these is a lone pair, which causes more repulsion because of its shape. So that is more likely to be about 118 rather than 120. Okay. Right. 2. Let's talk about ionization energies. Okay, so we have got helium, lithium, and beryllium. The first ionization energy, to look at the electronic structures we need to consider, 1s2, lithium is 1s2, 2s1, and beryllium is 1s2, 2s2. And it wants the ionization energy in order of increasing. Okay, so we want the biggest one last. Now helium is going to be the biggest one. I'll tell you why in a minute. We'll explain why in a minute. So it's going to be that one or that one. Why is helium's the biggest? Well, it's because the electron is in 1s, not in 2s, so it's closer to the nucleus and there's no shielding. So that's going to be much bigger first ionization energy. Next, we need to consider which is going to be the order for these two. Well, the electron, they're both losing the electron from 2s, but for lithium, so the shielding is about the same. The distance to the nucleus is not that different, but lithium is going to be lower because beryllium has got 4 protons in the nucleus, bigger nuclear charge. Lithium atomic number 3, it's only got 3. So the answer, this one here, is beryllium is the second highest, so that is the answer. The second ionization energy of calcium has a magnitude of 1150. So not telling us the sign. Well, ionization energies are always endothermic, so it's got to be a positive sign. Let's remember that. So some of them are not, so it's going to be either that one or that one. The second ionization is when you remove the second electron. So calcium's already lost one, so it's a calcium ion losing one more. So B is the answer. Okay, that's the answer. It's not this one because that's got the wrong sign, hasn't it? The formation of potassium ions can be represented by this equation. Okay, now the state symbols are really important here. Which corresponds to the energy change? Well, it's not the first ionization energy because this is a solid. And the definition of first ionization energy is to remove electron from a gaseous atom. So what we've got to do first of all is, the first thing you're doing is going to calcium gas, and then you're losing an electron. Okay, so this one is the atomization, delta H at, and this is the first ionization energy. So we've got to look for those two. It's not that one, it's not that one. Well, it's definitely not electroinfinity, that's sticking an electron on. The sum of the atomization and the electron affinity, no. The sum of the atomization and the first ionization energy, that is the right one. Okay, so you've got some ions, and you've got three ionic solids. We've got dx, do that. We've got EY, and we have got GZ. Right, deduce the order of magnitudes of the lattice entropies, giving the most exothermic first. Well, this is lattice entropy of formation. Well, the answer is the biggest one is going to be GZ because it's got a double charge on both ions. So the electrostatic attraction is going to be stronger. It's going to be much stronger. And then it's a competition between the yellow one and the green one. Well, if we look at the yellow one, dx, that's going to be the next biggest one because they've got dx has got smaller ions than the other one. If the ions are smaller, they can get closer together, and so you get bigger, stronger electrostatic attraction. Okay, and the justifier answer, and EY is the lowest, yeah. Okay, now here's a Born-Haber cycle, and this is, I think this is kind of quite a typical specimen paper sort of question because I've never seen one quite like this, where they've tried to make it deliberately confusing by not showing all of the steps. Okay, so what we've got to do is we've got to calculate the second ionization energy of calcium. Right, so let's see what we've got. Now this step here, that's straightforward. That's delta H, formation of calcium chloride. So I'm going to put minus 796 down for that. This step here is pretty straightforward. This is the lattice entropy of formation of calcium chloride. So that is minus 2258. This step here, well, that's confusing because we're doing two things. We're atomizing the calcium. If you look, the state symbols changed there. So that is going to be, you have to put in the atomization of calcium. Is it gone? 178. But we've also atomized chlorine, Cl2 to 2Cl gas. Right. So that is 2 times the atomization. So that's going to be 2 times 122, that's 244. So that's 178 plus 244 for that change. Rub that out together, 178 plus 244. It's 422. Right. Now let's look at this one, which is the really confusing one. I'm doing orange. What's going on there? Well, the calcium is losing 2 electrons. Let's call that X. Okay, so X is equal to the first ionization energy of calcium plus the second ionization energy of calcium to get the second electron off. And then we're sticking electrons onto chlorine to form Cl-, and there's 2 of them, so it's 2 times the electron affinity of chlorine. That's what X is equal to, because it's quite a lot of different things. Right, so let's put the numbers in. X then is equal to, the first ionization energy they tell us is 590, and plus 2 times minus, this is minus 349, the electron affinities, so X is equal to minus 108 plus the second ionization, I missed the second ionization energy out there, the second ionization energy, that's what we've got to try and find out, okay? So now we need to use the diagram to find out what X is. Well, that's not too bad, because what we can do is you can say, right, that bit there is 796 plus 422. Don't worry about the sign as we're going against the arrow. So that's 796 plus 422. And that's 1218. And we know this one is 2258. So X is going to be equal to, I'll do it in black up here, X is equal to 2258, that one minus that one, 1218, which is equal to 1040. Now we can put that number into here, X, so that's 1040. And so the second ionization energy is going to be equal to 1040 plus 108, which is equal to 1148 kilojoules per mole. A quick common sense check, it's got to be bigger than the first ionization energy, and it is. That's only 590, so if it was less than 590, we'd know we'd definitely gone wrong somewhere there. Okay, so as I say, that was a very confusing question, I think. Normally, if you look at nearly any of the past paper, they show every single step for the Born-Haber cycle, and that's, you know, because that's the clearest thing to do. Right. Now, vanadium, transition metal. Okay, so the electronic configuration of the vanadium atom is we'll have to complete it. Right, so if you look in your periodic table, vanadium is that you've got calcium, you've got potassium, so that's 4s1. You've got calcium, which is 4s2, and then you've got scandium, titanium, and then vanadium. So that's 4s2, 3d1, 3d2, 3d3 for vanadium. So we're going to put down the 3d3, 4s2. Put the 3d first, because of course that's slightly lower in energy and it's got electrons in it. So when it's going to lose electrons, it's going to lose 3, it's going to lose 2 from 4s and 1 from 3d. So that's going to be 3d2 for that. Right, and we need to know the colors of these things for later on. It's going to ask us about that. The table shows the standard electrode redox potentials for some half-cell reactions. Now, first of all, this is another strange thing they've done here, is all of these ones are in order, starting off with a negative, a bit more positive, but then this one is out of sequence, and they don't normally do that. They usually put it in the right place, but they haven't. Again, okay, so we have to be careful there. Right, explain using the information the color changes that take place when SO2 gas is bubbled through a solution containing the dioxovanadium ions. Well, the dioxovanadium ion, the VO2 plus ion, so it start off, it will be yellow. And we're going to bubble SO2 through it. Well, will anything happen? Now, so we need to look at 2 half equations we've got there with SO2 in, so that one, and the one with the dioxovanadium, that one there. Now, Which is the most positive of those is obviously this one. So that's going to be the best at taking in, sorry, it's not the most positive, is it? That's the most negative. The most positive is this one, because they're not in sequence. So that's going to be best at taking in electrons. So that one is going to go forwards, because it's taking in electrons there. Positive can take in negative electrons. This is the most negative, so that's best at giving away electrons, so it's going to push them out. So the SO2 is going to reduce this one to this one, which is actually a blue color. Okay, so then it will turn blue due to the presence of the VO2 plus ion, the +4 oxidation state. And actually, if you do this reaction, you probably don't know whether they give you a mark for this, but into halfway through, you'd look green, because you have a mixture of yellow and blue, and it does do that. But you'd probably be forgiven for omitting that. Right, so now we need to see if this blue VO2 plus ion can react. Rub this off. So the two half equations we need to look at there again are, we need to look at the sulfur dioxide one, and we can see if this can react with this one here. So which is the most positive of those? Well, it's this one, so that's going to go forwards to form the V3 plus ion, which is green. And this one is the most negative, so that's going to push the electrons away from it and give them to the vanadium. So then it's going to turn green, because you're going to form the V3 plus. Now we need to see if the sulfur dioxide can react with the V3 plus. Okay, so the two half equations we want are this one and this one. Right, now which is the most negative of those ones? Well, it's not the sulfur dioxide one, it's this one. So this is going to be the best, hang on a minute. This is going to be the best at pushing away electrons. And this one is going to be the best at taking in electrons. So can SO2 react with V3 plus? The answer is no. The exact opposite happens. In actual fact, sulfate will oxidize the V2 plus back to V3. So then no further color change then after that. No further reaction. So the SO2 is a strong enough reducing agent to reduce it from the +5 to the +4, then to the +3, but not to the violet 2 plus. Okay, use the information whether the disproportionation of V2 plus into V3 and vanadium metal is feasible under standard conditions. Right, let's have a look at the two half equations we need there then. Right, so we're looking at the two half equations with V2 plus in. So we want this one and this one. Which is the most negative of these? Well, it is the top one. So that is the best at pushing away electrons. So vanadium metal will go that way. And this is the most positive, so that will take in electrons. So the answer to this question is vanadium will react. We expect it to react with V3 plus to form 2V2 plus. But that is not disproportionation. That's the exact opposite of disproportionation. So the reverse reaction can't occur. So no, it will not disproportionate. And if you think, how on earth do I explain that? If you look in most mark schemes, all you'll need to say is that you just need to say that the electrode potential of V3 plus V2 plus is more negative than that of the V2 plus vanadium. It's sorry, less negative. Less negative, that's all you need to say. You don't have to explain it in English, as it were. Okay. Right, this is a question. Okay, so copper sulfate reacts with an excess of aqueous ammonia to give a dark blue solution, and the dark blue solution contains that. They haven't given us the formula of that. You probably know what the formula of that is already, but we've got to work that out. Okay, and they're going to determine the complex of that by colorimetry using this method. So they're going to mix different amounts of ammonia with copper ions, okay? And so they're going to know the moles of ammonia and the moles of copper. Okay, and filter the mixture, any precipitate forms, ignore that. The filtrate is a dark blue solution, okay? So we're forming this complex ion, and we can put it in the colorimeter to measure the absorbance. So the bigger the absorbance, the darker the blue the solution will be, and so the more of the complex we have, okay? Now, what we're trying to find out is the molar ratio here. So if we find out that for 1 mole of copper, we need 2 moles of ammonia to make the darkest blue solution, then that would tell us that value of X there is 2. If on the other hand we needed 3 times many more moles of ammonia than copper moles to make the darkest blue solution, then it would be 3, and so on. Right, so it asks us, it gives us the results, okay? So you keep the volume of copper the same here. That's the same every time. And so we can work out the moles of that, and they're going to ask us to work out that. So moles is going to be conc times volume. So it's 0.5 times 5 over 1,000, which is equal to 2.5 times 10 to the minus 4, I think. Yeah, 2.5 times 10 to the minus 3, sorry. All right, we'll use that later. And then we're increasing the amount of ammonia by 3 centimeters cubed every time. So you're getting more moles every time you do that. The water, they're just adding that to keep the total volume the same, because otherwise you would be diluting the thing. So that's just to keep the water changes. If you look, every time 2 plus 18 is equal to 20, 5 plus 15 is equal to, and so on. That's just to keep that the same. And then they measure the absorbance. So you can see here with when you add 3, you get a low absorbance. When you add more ammonia, it goes up. When you add more ammonia again, it goes up even more. But then when you get to here, it doesn't go any darker blue. So that means at this point we've added enough NH3 moles to react with the copper, and we want to find out. It's obviously somewhere between 3 and 4 there, and we've got to find out what it is. So it tells us to plot a graph of absorbance against the amount of ammonia. So I've done that. Okay, so you can see the absorbance increases as you've got more ammonia, and then it levels out once you get to 12. It doesn't, the blue doesn't get any darker around this point as it stays. It's a flat line. Okay, so it tells us to extrapolate this line forward, the yellow line, and then the green line back, and we want to find out where they meet. That is when you've added just the right number of moles of ammonia. Now that is almost exactly on 10 centimeters cubed. Okay, so use the graph to turn the smallest volume of ammonia, so it's equal to 10 centimeters cubed. Moles of CO2 we just calculated before. We said that was 2.5 times 10 to the minus 3. Moles of ammonia, well, so we've got concentration times volume. This is moles of ammonia. The concentration is going to be, it's 1 mole per decimeter cubed of ammonia multiplied by volume 10 over 1,000. That is equal to 0.01. So we've got a ratio of copper 2 plus to ammonia moles there of 2.5 times 10 to the minus 3 to 0.01. Divide by the smallest number, you get 1 to 4 ratio. Okay, so the next part of the question, use this to find out the value of the ammonia. So we know X, we need X is equal to 4. We need 4 moles of ammonia for every 1 mole of copper 2 plus. And then it told us it was an octahedral complex. So that means we must have 6 ligands altogether 4 of them are ammonia, so that means the other 2 must be water, so Y is equal to 2. That's a pretty unusual question, I would have thought. Typical sort of specimen paper question. Okay. Right, the precipitate formed when some mixtures are made is copper-2 hydroxide. Write an ionic equation to show the formation of copper-2 hydroxide from its ions. Okay, include state symbols, so that's just going to be C, copper 2 plus ions, aqueous. What's the formula of copper 2 hydroxide? You obviously need 2 hydroxide ions because they're both 1 minus. So you're going to need 2 OH minus aqueous to form that. Right, I don't think it's looking for particularly for the copper, for the real complex, which you write as H2O4 OH2. I don't think it actually requires that. It's not clear. Again, normally they'd make it absolutely clear if they wanted the formula of the complex or just this simplified. They haven't really made it clear there. Okay. Right. Chlorine and bromine are elements in group 7 of the periodic table. Both exist in a number of different oxidation numbers and involved in redox reactions. Equation for the reaction between chlorine and cold dilute sodium hydroxide. Well, it's a disproportionation reaction. This is, you should know this, and it's just a recall. So it's going to be sodium hydroxide plus chlorine, and you form sodium chloride and sodium chlorate. It's chlorate 1, that is, and you're going to need a water. So to balance that, we are going to need 2 of them. If you just look at the oxidation numbers, it's 0 for there for the chlorine, -1 for the chlorine there, and +1 for the chlorine there. It's a disproportionation reaction that you definitely need to know that one. Okay. This reaction you don't need to know about, you've got to work out what's going on. Chlorine dioxide reacts with cold dilute aqueous sodium hydroxide. Okay, the equation is that. Using oxidation numbers, explain why this has undergone disproportionation. Well, the oxidation number of chlorine in ClO2, well, oxygen is always -2, so it's got to be +4 there. What's the oxidation number in ClO2 minus? Well, the sum of the oxidation numbers is equal to the charge and the species. So I would do the charge and the species is -1. Chlorine we don't know. Oxygen is always -2, so that's -4. So chlorine has got an oxidation number in that of +3. So it's +3 there. And let's do it for this one. What's the oxidation number there? You probably know it's 5 already. It's called a chlorate 5 ion, but let's just work it out. Sigma of the oxidation number is equal to the charge. The charge is -1. Chlorine we don't know. Each oxygen is -2, so that's -6. Chlorine is equal to +5. So that one has been oxidized up to +5, and this one is being reduced to +3. Okay, chloride ions can be oxidized to chlorine molecules by manganate ions, manganate 7 ions. The dilute solution of manganate 7, now that tells us without working it out, the oxidation number of manganese there has got to be +7 in that ion. And an excessive dilute sulfuric acid is added. As the manganate ion solution is added, it changes from purple to colorless. The formula of the manganese species during this reaction, again, you should know that it goes to the Mn2 plus ion always, okay? Next bit, using oxidation numbers, deduce the molar ratio of manganate to chloride that would appear in the balanced equation, right? So manganate is +7 there, and that's going to go to a +2 oxidation state. So that means it has been reduced. So that means, and that's gained 5 electrons because it's gone from +7 to +2. Let's have a look at chlorine. Cl minus is going to go to, I'll do it as half Cl2. Well, that's going from an oxidation number of -1 to 0. So each one has lost 1 electron. So you're going to need 1 manganate ion to 5 chloride ions in the balanced equation. Okay. And if you wanted to end up with not 2.5 Cl2, then you'd probably use 2 MnO4 minus to 10 Cl. Then, you know, this is then going to give you 5 Cl2 in the final balanced equation rather than 2.5. So either one of those answers is fine. Right. Potassium bromide reacts with concentrated sulfuric acid. 3 of the products of the reactions are hydrogen bromide. Now, this is confusing as well because right, that's the sulfuric acid is acting as an acid, but you'll also get bromine. The sulfuric acid is acting as an oxidizing agent there, and the sulfuric acid has been reduced to sulfur dioxide. So the one in red is an acid-base reaction. These two in blue, they're products of a redox reaction. Why does the hydrogen bromide, which is a colorless gas, appear as misty fumes when it makes contact with moist air? Right, it dissolves in the air. It's very soluble. Sorry, dissolves in water in the air and forms droplets of HBr in aqueous solution. And that's what the steamy fumes are. You wouldn't really be familiar with that with HBr, but with HCl, you know, HCl fumes are always steamy fumes, and it's the same. The type of the reaction, the formation of sulfur dioxide, well, it's redox because you've got H2SO4 and that goes to SO2. Oxidation number there of sulfur is +6, here it's +4. So the sulfuric acid has been reduced to SO2 there. Right, now I think that is about as far as I'm going to go with that paper, and I'm going to cover the second half of it in the next video.